Welcome to the second lecture of the course Applied Stochastic Differential Equations. The topic of this lecture is Ito calculus and stochastic differential equations. We will start by an introduction to the stochastic integral of Ito. The Ito integral is the generalization of the problematic integral that we saw already during the last lecture. We will attempt to define the integral using the Riemann definition, the Stieltjes definition and Lebesgue definition, but we will notice that all of these attempts will fail. So that's why we need to invent another new integral called Ito integral. Then we will take a look at the Ito formula, which is the formula used to replace the chain rule in ordinary calculus. Then we will rederive the solutions to linear SDEs by using the Ito calculus instead of the heuristic arguments used during the last lecture. Then we will take a look at nonlinear SDEs, their solution existence theories, and other things that we will come back during the later lectures. Finally, we will summarize the lecture. Let's start with the stochastic integral of Ito. So, during the last lecture, we already treated SDEs as white noise-driven differential equations of this form. So, it turned out that for linear equations, this approach was fine. So we essentially used classical ODE theory to treat stochastic equations by pretending that, for example, the white noise process is actually an ordinary function, which is actually not. For that reason, there was something strange going on, as we saw. So for some reason, the use of chain rule of ordinary calculus led to wrong results in deriving the covariance equation even for linear SDEs. But with nonlinear differential equations, we didn't have anything to start with even to make sure that we don't do anything completely wrong. And also the existence theory had some problems because the Picard-Lindelöf theorem assumptions were not met because the white noise was discontinuous everywhere. And actually the source of all of these problems is the everywhere discontinuity of the white noise. Now the question is that how should we then formulate SDEs such that we don't encounter these theoretical and practical problems? Let's now take a bit closer look at our stochastic differential equation. So what we have is that the time derivative of x is equal to some function of x and t plus some matrix L which is function of x and t, and it multiplies the white noise w of t. Let's now formally integrate the differential equation from t0 to t. This gives x of t minus x of t0 is equal to the integral of fxt dt plus the integral of L times W dt. Now we have two integrals there. The first integral is just a normal Riemann or Lebesgue integral, or definable under those theories, because f is just some function which can be assumed to be continuous in both variables, and the integral is just over t. The second integral is more problematic because we have the white noise inside there, and actually the integrand is non-continuous or discontinuous. It turns out that this integral cannot be defined as Riemann integral, Stieltjes integral, or Lebesgue integral, and we will take a look at that why it's the case. So let's now first attempt to define the integral as a Riemann integral. In the Riemann sense, the integral would be defined like this. So the integral is the limit of L times W times the difference of tk plus 1 minus tk. And the integral is defined to be the limit of this expression, where this limit needs to be unique in certain sense. The uniqueness in the Riemannian case means that the upper and lower sums need to converge to the same value. And upper and lower sums are defined to be selections of t star such that the integral L x of t star w t star has its maximum value or minimum value at these evaluation points. So the upper sum corresponds to maximum and lower sum to the minimum. And the Riemann integral exists if the upper and lower sums converge to the same value. And now what happens is that we are actually evaluating the value of white noise over there. And it is discontinuous everywhere, which means that there is no hope that the upper and lower sums would actually converge to the same value. And that's why the Riemann integral cannot exist in this case. So we cannot define this integral as a Riemann integral. As the second attempt, let's take a look at Stieltjes integral then. The Stieltjes integral is more general than Riemann integral because, at least in limited sense, it allows for discontinuous integrants. Now we can interpret the increment Wt times dt as an increment of another process, let's say beta t, such that we have the integral of L Wt dt actually means the integral of L d beta. It turns out that the suitable process for this purpose is the Brownian motion. Let's now take a look what the Brownian motion process mentioned in the previous slides actually looks like. The Brownian motion beta of t is a process such that the increments are Gaussian. So if we define the delta beta k to be beta evaluated at tk plus 1 minus beta evaluated at tk, then these increments are normally distributed with mean 0 and variance or covariance given by q times delta tk, where this delta tk is the difference of the time instance. It's noticeable that the covariance actually scales with linearly in dt instead of quadratically in dt. And it turns out that these non-overlapping increments are independent. So provided that you don't have the same time points shared between the intervals, those increments are independent. On the right you can see an example trajectory of a Brownian motion. So it's basically a continuous version of a random walk. And actually it was originally constructed as a mathematical description of a continuous time random walk. Now here Q is called the diffusion matrix of the Brownian motion, in the same sense that we called Q as the spectral density of the white noise. Actually it's exactly the same parameter, but anyway it's called diffusion matrix here, due to the different physical interpretation. The Brownian motion process as function of t is discontinuous in derivative everywhere. The Brownian motion as function of t has discontinuous derivative everywhere. In the same sense everywhere as white noise was discontinuous everywhere. But here beta only has discontinuous derivative, so it is actually a continuous process still. And the connection to white noise is that white noise can be considered as the formal derivative of a Brownian motion. So when Brownian motion has discontinuous derivative everywhere, it means that the derivative, which is the white noise, is discontinuous everywhere. So using this defined process, let's now attempt to define our integral as the Stieltjes integral. So in Stieltjes case, we should define the integral of L dB as the limit where we have L, x and t times the increment of beta. And then we take a suitable limit of the number of time points to go to infinity. For the integral to exist, we should have the property that this limit should be independent of the t star selection on those small intervals. And then if this limit is unique, the integral exists. But it turns out that for integration with respect to Brownian motion, this will not be the case. Because the process has discontinuous derivative everywhere, it turns out that this limit will not be independent. Thus, even the Stieltjes integral definition doesn't work. As the third attempt, we can now try to define our integral as a Lebesgue integral. In Lebesgue integral, we can try to interpret beta t to define a stochastic measure by saying that the measure of interval u to v is equal to bu minus bv. Essentially, this will lead to this kind of definition. So the integral of L x and t dB is equal to the limit of L x evaluated at t star and t star times the increment of beta. Again, for the integral to exist, this limit should be independent of the choice t star at each of the small intervals. But it turns out that that will not be the case due to the non-differentiability of the Brownian motion. Also, our measure is not really sensible because the increments or the measures of intervals will also be negative sometimes, actually very often. So it turns out that the Lebesgue integral doesn't work either for this case. Our fourth attempt is the Ito integral, which actually turns out to work. So the solution to this integral definition problem was already proposed by Ito in roughly 50s, and it's nowadays called the Ito stochastic integral. The basic idea is to recall that actually the problem in the definition was that the limit was not independent of the choice of t star in those small intervals from tk to tk plus 1. So the idea of Ito is that let's not attempt to compute the limit for arbitrary t star in that interval, but let's choose the beginning of the interval as the evaluation point. So the integral of L d beta is defined as the limit of L evaluated at x tk and tk times the increment of the Brownian motion. It turns out that this definition is sensible in the sense that we have a unique limit. However, we have the downside that the resulting integral definition does not obey the computational rules of ordinary calculus. So instead of the ordinary calculus, we will have something called Ito calculus. So for example, we will need to change the chain rule completely. So let's now take another look at the stochastic differential equations. So we have a white noise driven ODE of this form. So the time derivative of x is equal to f of x and t plus L x and t times the WT. But as we saw that this actually should be defined as the Ito integral, where we have xt minus xt0 is equal to the integral of f dt plus the integral of L d beta, where this d beta is the increment of a Brownian motion. And that's how Ito SDEs are actually defined. So they are actually Ito integral equations instead of Ito differential equation. So in very short intervals, we can define a shorthand notation like this. So we call xt minus xt0 as just dx, then remove the integral sign from f integral and integral sign from the second integral. So we will have this kind of differential notation for Ito SDEs. And this is the canonical form of Ito SDE that we usually see. We can now formally divide by dt, which gives something like this. So dx over dt is equal to f x and t plus L x and t times d beta divided by dt. So if we compare to our white noise SDE, we can interpret d beta dt as a white noise process. Well, we already saw in the definition of Brownian motion that the white noise is a formal derivative of Brownian motion. And this is exactly the same property. Also notice that because we actually had to define SDEs via the corresponding integral equation, we have no way to define this type of very general stochastic differential equations where the white noise enters arbitrarily nonlinearly on the right hand side. So we can certainly multiply W with L, but we cannot have a square of W or anything like that on the right hand side, because it cannot be translated back to the integral equation definition. And for a similar reason, the white noise should not be thought of as an entity as such, but it only exists as some kind of formal derivative of Brownian motion. In practice, we can put white noises into models, but we need to recall that it's not permissible to, for example, multiply white noises or put white noises inside arbitrary nonlinear functions, because white noise is not a function in the same sense as ordinary functions.